Okay, welcome everybody to today's talk in the Laws of Nature series. I'm happy that so many of you came today. I'm going to announce our speaker, Daniele Oriti. He's now currently working at the Physics Institute of the LMU Munich. He has a Heisenberg grant, so his own working group there. He's also attached to the Munich Center for Mathematical Philosophy as an associate member. And he's researching on quantum gravity and foundations of physics in general. Starting from next April, I think he's going to move and have a full professorship in Madrid, in Spain. I'm happy that you come to our series and talk here, and you will talk about quantum gravity, hydrodynamics, and cosmology. So please, go ahead.
Thank you. So thanks for being here. Thanks for the invitation. I could have chosen two topics mainly for this seminar. Another possibility, not the one I'm going to focus on, would have been to focus instead on the idea of emergent space-time in quantum gravity. But I can promise that you will see some of that here as well as part of a broader story. So let me go, and you always start with some motivation. So let me tell you what is my motivation for trying to connect quantum gravity, cosmology, and hydrodynamics. So although I work on quantum gravity, I pretend to be a physicist. And so I start with some physical motivation coming from cosmology. And the main point is that despite the amazing picture and detailed picture that
menu bar will disappear eventually.
Yes. Despite the amazingly detailed picture that theoretical cosmology and observational cosmology give us about the universe, there are a number of outstanding challenges, and with different degree of arguments. Most of these outstanding challenges call for a quantum gravity completion of the history of the universe and of theoretical cosmology, or to put it differently, they call for an embedding of cosmological models within a more fundamental quantum gravity formalism. And this type of embedding is called for at two levels. In early cosmology, all the existing cosmological scenarios, starting from the most successful scientifically and sociologically, which is inflation, but even more clearly in other cosmological scenarios like bouncing cosmology or emergent universe, they all call for new physics in the very early universe, either directly replacing the Big Bang or at least clarifying what is going on at the very origin, so to set up proper initial conditions and make sure that new effects coming from around the Big Bang physics don't spoil the later setup, for example, of inflationary models. In alternative scenarios like bouncing cosmology, where the Big Bang is replaced by a bounce, or emergent universe, where the Big Bang is actually replaced by a phase transition from a static universe to an expanding one, clearly new physics is needed because none of these scenarios can be realized fully within effective field theory, standard quantum field theory on curved spacetimes. But this is just one set of arguments. Then other outstanding challenge in cosmology concern the late universe evolution, dark energy, so the observed accelerated expansion of the universe, which is less directly obviously linked to quantum gravity. But the fact that it's less obvious to call for quantum gravity in explaining dark energy has to do with the assumption that the effective field theory framework is valid at the more fundamental level with its separation of scales. So if that is true, then we tend to say, well, quantum gravity is small distance scales, large energy scales. Dark energy is the other side of the story, is very large distance. So it will not be quantum gravity, but that's an assumption. In a number of quantum gravity approaches, the whole cosmological evolution, the whole notion of space-time and geometry is in fact an effective collective notion from quantum gravity degrees of freedom. And so even late time acceleration could be a direct product of that. We will see an example later when I will try to keep my promise to say something about the whole emergent space-time ideas in this context. Okay, set of motivation, cosmology needs quantum gravity, or let me add, probably needs quantum gravity. When you look at quantum gravity, we find in a sense a complementary challenge. There are a number of quantum gravity approaches. Again, there are more successful, more widespread approaches, more niche-like directions. But there is definitely a diversified landscape with many results, many conceptual insights, some rigorous mathematical formulas being developed. But if I had to indicate one outstanding challenge in basically all of them, is exactly to connect to effective field theory, to standard physics, and in particular to cosmology. The challenge is partially met in some approaches, but is always still outstanding in all of them. The details of the challenge and the detail of the proposed solutions will then vary from one approach to the other. But broadly speaking, the challenge is out there for all of them. How is the challenge met? Well, of course, from some quantum gravity approaches, there are attempts to derive within the main formalism, within the fundamental framework, effective cosmological dynamics. But otherwise, people work with toy models directly tailored to cosmology and only importing ideas from the fundamental formalism, or similarly with phenomenological models, again, constructed to deal with cosmology, but inspired or incorporating ideas from fundamental quantum gravity formalism. But there is a gap still between such toy or phenomenological models and fundamental quantum gravity formalism, and bridging the gap is needed to really constrain the fundamental theories, make them testable, and I don't want to say falsifiable, that's too much, but really no, corroborated to different degrees by observations. How to connect the two? Well, before I show you how to find a link, let me try to give an idea of the magnitude of the challenge from a quantum gravity point of view. So this is just one example. In a number of formalisms, loop quantum gravity, spin forms, group field theory, lattice gravity, what is suggested to replace the smooth manifold of field theory, the very notion of fields as fundamental entities, including the geometry, including the metric field, is purely combinatorial algebraic structures. For example, spin networks are suggested in some formalism, in fact, in all of this, in one way or the other, to be the quantum states of geometry, of space-time at the fundamental level. Now, what is important here is not to understand the detail, but just to understand that the statement is, forget about the manifold fields and all that smooth structure, classical or quantum. The fundamental stuff, mathematically at least, is some network-like excitation, purely combinatorial, decorated with algebraic data. Then, depending on the model, depending on the formula, the details will change, but that's the main message. So now you should be able to see the gap. From that type of structures, you have to reconstruct smooth fields, living on a smooth manifold with all the usual classical and quantum mechanical description. And I want to emphasize, again, to make you appreciate the difficulty of what are the conceptual issues there, even before I try to convey some of the mathematical details. that the problem of extracting an effective continuum picture is conceptually and technically different from the problem of extracting a classical approximation from the fundamental theory. Think of a quantum many-body system. There are two things you can do starting from the many-body Schrödinger dynamics. One is to take a classical limit. Then what you're going to get is a classical theory of many bouncing particles with different data. Okay, if they have spin, if they rotate, the Hamiltonian could be different, but that's what you're going to get. Then you can take a continuum limit, which basically means studying the coarse-grained, macroscopic, collective dynamics. And in some cases, it's going to give you hydrodynamics, classical hydrodynamics. From many classical particles swirling together, you get some fluid, classical fluid. Go back to the same initial point. You can take instead first the continuum limit, again, study coarse-grained behavior, collective behavior, and so on. You may end up with a quantum fluid, a Bose-Einstein condensate, a superfluid, superconductivity, all of that, and a number of topological phases, purely quantum, depending on the system. At which point you can take a classical limit if you want, and a lot of effects will become negligible in that limit. And maybe you get, you commute and you go back to a classical fluid. But in general, the two limits not only are different technically and conceptually, but they don't commute. They don't commute. And if you mistake the two limits, the two approximations to be the same, you miss a lot of physics. In quantum gravity is the same. Many formalisms propose some new type of quantum degree of freedom from which you have to extract from collective behavior, continuum limits, the usual field theoretic story, still quantum. The two limits may not commute and they may not have to go together. Is this point clear conceptually? Because it's important for what follows. Okay. Cosmology, quantum gravity. Well, how to connect the two? I'm going to suggest and give some arguments why that at least convince me that a way of connecting the two is through techniques and ideas from hydrodynamics. And this is take them as three directions, three areas of research that one can try to connect. The three petals of a trefoil. But I would also argue, and again, I will tell you why I am convinced that we can be lucky and there could actually be a quatrefoil waiting to be picked, in which a fourth leaf is given by analog gravity. So that, in other words, I will argue a little bit better later, that connecting the three in the way I will suggest also indicates a possible new directions for analog gravity simulations in condensed matter. Okay, a trefoil can be a quatrefoil if you're lucky. So more precisely, there are four statements I want to convince you of, or at least propose and show that they are not unreasonable, to be more modest, in the following. And the four statements are the following. First point, hydrodynamics, standard hydrodynamics, or if you want to be a little bit fancier, you go to the hydrodynamics of quantum fluids, which is not that different, can be mapped to relativistic cosmology, including the symmetries of the two systems. This is just a statement. The convincing part will come afterwards. The second statement is that cosmological dynamics, in fact, can be seen to emerge from quantum gravity dynamics, at least in some formalisms, as its hydrodynamic sector. And the whole theory, the whole formalism and hydrodynamics in particular, will be defined on what is called superspace, which has nothing to do with supersymmetry historically. Superspace is the space of fields, including the metric field. Okay, check Wikipedia. If the referee of my paper is among you, you can check on Wikipedia when the term superspace was introduced. And that's the way superspace, as the space of field configurations, including the metric, is used in the quantum gravity, quantum cosmology community by everybody who doesn't immediately think about supersymmetry. Then you can think about supersymmetry. That's fine, it's compatible, but then you have to be careful with the terminology. The third point is that through this connection, through these two facts, cosmological frameworks can be embedded in fundamental quantum gravity, and hydrodynamics provides the tool to do that, so to increase the predictive power and a testing ground, giving a testing ground to quantum gravity. The fourth statement that I hope I will have time towards the end is that analog gravity simulations, if all of that is true, analog gravity simulations do not need to be confined to the kinematical aspects of general relativity. As I will emphasize, at the moment, analog gravity simulations have to do with reproducing a given geometry and the dynamics of perturbations around it. From the point of view of general relativity, that's just the kinematics. They reproduce a given solution, but not the dynamics that provides that solution. And I will suggest that maybe that's not a structural limitation. We can do better. We can actually try to reproduce dynamics. Okay, I'll take the three challenges in one after the other. So first, standard hydrodynamics can be mapped to relativistic cosmology, symmetries included. I will keep flashing the same statement so that at least the statement is clear. Then the arguments, well, you can check the slides afterwards. Okay, forget about quantum gravity, forget about cosmology for a while. Take standard nonlinear Schrödinger equation, or in other words, non-relativistic hydrodynamics. This is the Grosspitesque equation for a weakly interacting Bose condensate. There is a condensate wave function. This is complex scalar field. There is a Schrödinger-like operator with some external potential, which is the trapping potential for your condensate. But it's hydrodynamics, and the system is interacting in general, and this is one choice of interaction. This type of equation is very difficult to solve. You simplify, go to a two-dimensional cylindrically symmetric condensate with a parabolic trapping potential. So the wave function, the condensate wave function, that is the fluid density, the velocity, and so on, only depend on two directions, radial and temporal. It's a fact that you can encode fully these dynamics in equations for some hydrodynamic averages, which are the integral moments. One is the energy. There is a missing term here. Trust me that there is the remaining part of the formula, and radial momentum, the particle number, and so on. There are a number of integral quantities you can compute from the condensate wave function. And you can show that they satisfy a set of coupled equations. And you can also show, first of all, that the set of equations is equivalent to a so-called Ermakov-Pinney equation. Okay, this is just mathematical physics cosmetics. But solving these equations is equivalent to solving the original nonlinear Schrödinger. Okay. Again, nothing to do with gravity, with cosmology, with quantum gravity, just mathematical physics. Physicists enjoying themselves. Play with the equations, find symmetries, moments, equivalent ways of rewriting them, and proceed. Okay, consider now cosmology. The Friedmann equations for the scale factor of the universe related to the volume of the universe, depending on time, on some coordinate time. In this particular case, is cosmic time. And having as a matter content some scalar field interacting with some potential, self-interacting. It's a very simple model of the universe, but it's pretty effective in describing a lot of phenomena. Everything is homogeneous and isotropic, so there is only the dependence on the time variable. Of course, this time variable is pure gauge. We have reparameterization invariance. You can change from cosmic time to what you can call, for reasons that will be obvious, laboratory time. Nothing changes, but this means that you can rephrase these equations into the same Ermakov-Pini equation that I mentioned earlier. Again, pure cosmetics, not changing the physics, and there's no other statement. You can just massage the equations, put one into the other, change variables, and so on. But you can take this a little bit more seriously, even if it were just for fun. And you can say, well, but if they satisfy the same equation, I can try to justify or keep going with this correspondence, and I can put in correspondence cosmological quantities, the square of the scale factor, the Hubble variable, with some particular functions of the integral moments, so that it's clear that they are going to satisfy the same equation. So there was a certain dynamic satisfied by the integral moments of an hydrodynamic system, with the same equation for the cosmological variables. And this can be seen to be also the result, if you want, of another mathematical formal correspondence, which is the set of correspondences between cosmological variables and integral moments of the hydrodynamic system. There's no claim here because the two systems are entirely different, but it happens many times in mathematics and mathematical physics that you end up with the same equation describing very different systems. Okay, so it's a fact. It's just a mathematical coincidence, possibly, but it's a fact. Well, it's a bit more than that, because in fact, you can show that also the symmetries of the two systems are the same. And that is more surprising if you come from general relativity. First of all, look again at the nonlinear Schrödinger dynamics. Now I can write the action for the same dynamics I gave earlier. And you can show that there are a set of transformations. This is a standard system, a fluid living on a space-time manifold with two directions, time and space, radial direction and time. There are some symmetries, and the symmetries are the non-relativistic ones you would expect, translation, Galilean boost, rotations. But then the system is also conformal invariant. It has dilatation symmetry and some conformal symmetry. And you can write down the generators and use them to solve the dynamics of the theory, or to fully encode it in terms of transformation generated by such quantities. Okay. Then you then you go back and say, okay, but the same dynamics with these symmetries was in cosmology. Then that's probably where the analogy breaks, because in cosmology, we have homogeneity and isotropies that basically kill most of the diffeomorphism symmetry under change of coordinates, reparameterization. I'm left just with the time reparameterization, which is none of this here. There's no such reparameterization here. And what else? I mean, in the Friedman case, nothing else. I would not pose things in this way if there was not something else, right? So there is something else. In space-time systems, there are, of course, the space-time symmetries, which are all subgroups of diffeomorphism having to do with changing coordinates and transforming things on the manifold. But in fact, there are also symmetries that have to do with transformations acting directly on the space of fields. For any given point on the manifold, you look at the space of field configurations at that point, and you can check if there are transformations of the values of the fields coordinated that leave the system invariant. In fact, these are the symmetries we care about here. And there is a general mathematical procedure that is very nice, is a geometrization of mechanics to find those symmetries. And the general idea is the following. You take a generic mechanical system. This is classical mechanics. You have some dynamical variables. So there is only a temporal coordinate, and there is a finite number of variables, chi. you can rephrase the system as the motion of a point particle on superspace, the space of configurations of the dynamical variables, the space of chi's, possible values for the variables chi, chi1, chi2, depending on how many you have. That space has a metric. That metric is the supermetric because it's the metric on superspace. So you can show that the dynamics governed by this action can be seen as the dynamics of this action, that is the dynamics of a point particle on the space of configurations. Okay, with this? Again, this is just mathematical rewriting of things. But it's useful because you can also show that when you look at time-independent transformations, symmetries of this mechanical system, the solutions correspond to geodesics of the conformal supermetric. So you just look at the conformal Killing vectors of the supermetric in this rewriting, and they correspond to transformations of the variables of your mechanical symmetry, your mechanical system. So symmetries of your mechanical system. So they are conformal isometries of the supermetric. You can further extend the same description to include, to account also for time-dependent symmetries. And this is the so-called generalization of superspace to give the so-called Eisner-Duval lift. Is basically you take superspace, that was this part, and you extend it by two directions. But again, the story is the same. You have a point particle moving on this extended metric manifold. And the classical solutions of the original system correspond to null geodesics of this extended space. And the symmetries of the original mechanical system correspond to conformal isometries of the extended supermetric. Okay. So mathematical fact, but you can apply to Friedman, and to make a longer story short, because I have to, you can find that in fact, apart from time reparametrization that you can always gauge fix, they're just part of diffeomorphism, they're not really physical, they're just gauge, you can find that there are field transformations that still remain as symmetries of that dynamics. And it turns out, if you do the analysis, that these symmetries are exactly the two-dimensional centrally extended Schrödinger algebra of the hydrodynamic system I started from. So there is a match in dynamics, the equations, there is a match in the underlying symmetries of the system. And in fact, you can proceed the other way around. You can start from the cosmological model, you analyze the symmetries, you find the symmetries, and then you look and you reconstruct what would be the hydrodynamic system with the same generators. Of course, in the hydrodynamic case, the generator will be some average, some hydrodynamic average. But you can reconstruct what should be the hydrodynamic action and equation with the same symmetry so that it is in correspondence with your cosmological model. Could be mathematical coincidence, but well, then there are many coincidences because you can do it for a number of other models, both at the level of dynamics and of symmetries. So maybe there is something more to it. You can still believe it is a mathematical coincidence, but you can also be optimistic, and your optimism, you call it a research program. You can even get money for it. Not much. There are more lucrative jobs, but well, still. But then if you want to take it seriously, there are two main questions that you can ask, or a referee will be kind enough to ask. The first one is, what could possibly be the connection between the two? Okay, I understand the mathematical connection is deeper than I initially thought, but still, what could be the physical connection? And the second question, can this link be explained, supported, or derived from a more fundamental theory? Now, the first hint of what could be a physical connection is again at the level of cosmetics, if you want. Take the original hydrodynamic system and just call the radial direction A, like the scale factor, and your temporal direction phi as a scalar field that you can use as a clock in quantum cosmology or in deparametrized Friedman cosmology at the classical level. Well, then the map that we had before, not only about symmetries, but also the one between cosmological quantities and moments, is pretty natural. In fact, you are computing averages of cosmological quantities as you would do in quantum cosmology or in some statistical approach to cosmology. What were hydrodynamic averages would look like really taking expectation values of operators in some wave function, to which you can give a statistical interpretation, but again, formally is what you would do also in a quantum cosmology setting. This again doesn't prove anything, but it suggests that this correspondence between hydrodynamics and cosmology can at least become more plausible formally, so in the details, if you reinterpret the same hydrodynamics as being defined not on a manifold, on a space-time manifold, but on superspace, the space of fields. If you have hydrodynamics on superspace, then what you basically have is a nonlinear extension of quantum cosmology, and this statement will be only clear to people of you who know about quantum cosmology. The others can safely ignore the statement for a while. Okay, what about the second question? Can the same correspondence be motivated or explained or derived from some quantum gravity formalism? Yes, the second part of the talk is about this. There are quantum gravity formalisms whose hydrodynamic approximation, whose coarse-grained effective continuum description, takes in fact the form of hydrodynamics on superspace, or a nonlinear extension of quantum cosmology. Now, the statement was careful enough that I can say it's a fact, because I can give you which formalism and in which approximation gives you hydrodynamics on superspace as a result in an hydrodynamic approximation. How general that is, the fact that it's somehow significant beyond the specific cases that have been explored or beyond the specific formalism in which it has been realized, that remains to be seen. And I'm not making claims about that. I can make the claims, but I don't have the full story to support. Okay, now I'm going to show you this part, how you extract cosmology from quantum gravity models in one particular framework using the hydrodynamic approximation. Okay, so let me show you that. First of all, heuristically, I want to introduce the formalism before I give you more details. The basic ideas of the tensorial group field theory formalism is that you have a field theory, but it's not a field theory for particles or fields on a given space-time manifold. It's a field theory whose quanta, whose fundamental excitations around the Fock empty vacuum are sort of discrete building blocks of space. And you can see the following way. You can take a smooth manifold, chop it, and replace it by a lattice, a triangulation formed by tetrahedra or four simplices depending on the dimension. Okay, this is something that is pretty standard. I mean, a quantum gravity context, which is not standard, but the idea of discretizing your space-time manifold and every dynamical field living on it is standard. This is lattice gauge theory, is field theory in a particular way of formulating it. Okay, so but take this triangulation, this lattice, and look at the individual constituents, take them seriously, and now write down a field theory that has n-body state corresponding to such building blocks, and all possible n-body states corresponding to arbitrary numbers of such building blocks. So this replaces the particles or the quanta of ordinary fields on a given manifold. And this is true at the dynamical level as well. Normally you have a field on a manifold whose quanta are particles on a manifold. You expand perturbatively, and the elementary processes are Feynman diagrams embedded in a manifold that describe elementary processes, right? Two particles with their position or momentum scattering, bouncing off each other, or creating, annihilating new particles. If you do the same for this type of field theories, the Feynman diagrams are in one-to-one correspondence with lattices, space-time lattices, as you would use in lattice gauge theory. But these are the diagrams, the elementary discrete processes of interaction. And the Feynman amplitudes, the elementary amplitudes you associate to such elementary interaction processes in these theories take the form of lattice gravity path integrals. What you would write down on a given lattice as the discrete counterpart of a continuum path integral for the Einstein-Hilbert action, you write it in the discrete on a given lattice, and it appears as the Feynman amplitude for the diagram dual to that lattice in this field theory. Okay, these are the basic ideas. Now, the next step, again, at this conceptual level, at this general level, is to ask, okay, but if these are the elementary building blocks and the elementary interaction processes, where from comes space-time continuum and gravity and GR and so on? Well, the idea is that you have to look at a coarse-grained description of these elementary structures and at the collective quantum dynamics. So you're taking seriously this idea of space-time as a sort of a quantum many-body system. You have a microscopic atomic description, including the elementary scattering processes, and you look for an effective continuum coarse-grained description. Now, I don't give details, but they are here. You can ask. You can take an elementary building block being a tetrahedron in Euclidean geometry. You write down the phase space, all the geometry of the system, the phase space, and you quantize it. So you obtain a Hilbert space of all the possible states of a single tetrahedron, all possible areas of the triangles, all possible lengths of the edges, all possible volumes of the tetrahedron, and so on, all possible states at the quantum level of a single tetrahedron, including superpositions. It's a Hilbert space, okay? Then you use this Hilbert space to, you can write it in different representations, okay? That is more technical. You can use it to construct a Fock space of tetrahedra, or quantum tetrahedra, right? You have a single body Hilbert space. You take tensor products for n tetrahedra, and then you can superpose, you can consider all possible particle numbers. That's a Fock space. And you can move around states in the Fock space by field operators. You have a second quantized language for dealing with that, just like any standard quantum many-body system. And you can have also operators. For example, you can consider from the classical description the volume operator for a tetrahedron at the quantum level. There was a classical expression for the geometry of a tetrahedron giving the volume. There is a corresponding operator acting on a single body Hilbert space. And then you can second quantize, and you can have an operator given by the convolution with field operators, which gives you the total volume you can attribute to a generic ensemble of n tetrahedra by summing the contribution from each of them. It's no wonder that it's an additive extensive quantity. It's a bit like the total momentum of an n-body system. There is a momentum contribution from each atom, each particle, and then there is a second quantized formula for the total momentum of the state in the analogy. Okay, so you have a second quantized language for states made out of several tetrahedra. There is a corresponding dynamical story. You can write down an action that governs the dynamics of many tetrahedra that are scattered together. And it's going to be some complex scalar field with some kinetic term and some interaction term. Now, this is the formalism that I'm describing, not specific models. Are you still with me with the general ideas? It's not that you have to believe me, but you'll see what is the points that I'm making. Okay, I hope so, but feel free to ask if the answer to my question was no. Okay, and then as I said, for models in which you have the nice discrete geometry in place, all the right data, and you encode how you geometrically glue tetrahedra together, matching the areas, matching the edge lengths, and so on in the action. The result is what I anticipated, that the Feynman diagrams look like 4-dimensional lattices, while your building blocks were these 3-dimensional simplices, the tetrahedra. And the Feynman amplitudes can be written, if you choose the variables appropriately, as lattice gravity path integral. So you have a partition function, a Feynman expansion in diagrams, gamma, and the amplitude looks like the gravitational path integral discretized on the lattice dual to the diagram. Okay. Where from cosmology? Well, you could argue that not only you have to look for some coarse-grained description, some collective description of this quantum degrees of freedom, but cosmology should correspond to the most coarse-grained description, the one in which you basically only deal with global observables. You lose track of the local structure. It's really large-scale physics, right? So it's the total volume of the universe, the total curvature, the average curvature of all of space, I mean, the global stuff. And basically, that corresponds to an hydrodynamic approximation the moment you take the perspective of a quantum many-body system. You look at the most coarse-grained description, and that's basically hydrodynamics. Some global quantities still dynamical. You're not in thermodynamics where you just have structural relations, but there is still dynamics. The simplest approximation to the hydrodynamics you can take if you start from a full quantum field theory is mean field. So you have a full quantum effective action that will correspond to the full theory rewritten in terms of an effective action for a mean field from the expectation value of your field operator. Computing that amounts to computing the full partition function, so solving the theory and being able to compute any observable exactly. The simplest approximation to this, which is also the most used because we are poor men, is mean field, in which you neglect a lot of quantum corrections. And it basically corresponds to the classical action. Now, here, before I say, do I have 5 more minutes? Yeah, okay. I will need 10, but I will first use 5 on this quantum gravity story, and then I will use another 5 for the last part of the analog gravity suggestions. I just want to make one point clear. In the following, when I connect to cosmology, I will stay at this mean field level, which by construction means neglecting all the 1 loop, 2 loop, 3 loop corrections present in the quantum effective action that you would derive from the full field theory. Now, the classical action is classical with respect to field operators, but is highly quantum corresponding to the atoms or the particles. If this sounds crazy, think of classical electromagnetism. A classical electric field, or the gauge potential, is the collective wave function for a coherent state of photons, which is an infinite superposition of photons. So obviously, it is a classical quantity from the point of view of fields. but it's a highly quantum coherent state with respect to the quanta, the photons. And this is a general point, of course, that what you mean by classical limit or classical approximation depends on the observables. For something that is classical for some observable is going to be highly quantum from the point of view of other observables or other states. Anyway, so let's let me skip this in case I will tell you more. But now we take the following. We take these models in this tensorial group field theory formalism, restricting attention to those models which encode correctly the discrete geometry of the structures, the tetrahedra, the four simplices, the diagrams, lattice gravity, path integrals, and so on. And then two general facts follow. The first one is that you look at this condensate wave function, the mean field, and it's a complex function on a domain which you can show is isomorphic, in fact diffeomorphic, to the space of homogeneous special geometries, also known as mini superspace in quantum cosmology. So the dynamical variable in this mean field approximation is going to be a function, complex function, on mini superspace. And this follows from the fact that mathematically the space of geometries of a tetrahedron is isomorphic to the space of metrics at a point, which is the same as the space of special metrics being homogeneous. So the domain is the same as in quantum cosmology. However, other general fact, you're going to get mean field dynamics given by some equation, and the equation is going to be nonlinear because it's hydrodynamics, including some self-interaction of the mean field. So it's going to be exactly a nonlinear extension of quantum cosmology because it's a nonlinear self-interacting equation for a function on mini superspace. So those of you who know about quantum cosmology will say, well, quantum cosmology, we know that you have a wave function on mini superspace resulting from quantizing the homogeneous sector of general relativity, and there is a differential operator acting on it linearly, and that is the Wheeler-de Witt operator. Then you can change variables, you can do all sorts of fancy things, but that's basically the structure. Here you get a similar type of picture, but first of all, it is nonlinear, so there is a nonlinear extension, and it's not the result of quantizing general relativity, it's the result of coarse-graining quantum discrete building blocks and their dynamics, treated as a quantum many-body system. This is totally general, so if you want to write things in the language that I used earlier, you're going to get an equation like this. A function depending on the scale factor and some scalar field, if you have added those degrees of freedom, satisfying some nonlinear equation. And you can write down operators and ask what is the equation of motion satisfied, for example, by the expectation value of the volume operator or the scale factor in the condensate state. You had operators for the quantum tetrahedra, all sorts of geometric, discrete geometric quantities. You can ask about expectation values in such a collective state. Just like you try to extract equations for the total momentum of your fluid from the hydrodynamic equations. So let me skip the details. Let me just give you, you can do this for a number of observables and with all sorts of details. And what seems rather general for a number of models, at least it has been realized, is that you have an expanding dynamics for the volume resulting from this coarse-graining and directly from the fundamental dynamics of the theory, in which the Big Bang is replaced by a bounce. Then the universe keeps expanding and you get the nice Friedman-like dynamics. This is the Friedman equation written with respect to a clock, a physical clock, rather than a time coordinate. And then the universe keeps expanding, and with less degree of generality, you need some additional assumption. You can also get an accelerated expansion at late times. which is intriguing, but I don't have big claims to make here. Okay, I'll skip here. So we learn that an effective space-time geometric cosmological dynamics can be extracted from the fundamental quantum gravity formalism in the hydrodynamic approximation, and it takes indeed the form of a nonlinear extension of quantum cosmology or hydrodynamics on superspace. There are, of course, many things that are left to do from the quantum gravity point of view and also from the cosmology point of view. But at least I made my point that a connection that was purely at the level of mathematical physics, but was suggesting that a useful formalism for studying cosmology could be hydrodynamics on superspace is in fact realized from at least one candidate quantum gravity formalism, and is realized exactly, I mean, with all sorts of approximation, but exactly in this language. Now I conclude with the last 5 minutes. Good. Why this may have to do with analog gravity simulations in condensed matter. Forget about quantum gravity. Don't totally forget about cosmology, at least as a motivation, but the formalism you can partially forget. A general result, which is the sort of the origin of all the field of analog gravity in condensed matter, is the following, that you can take a fluid, classical or quantum doesn't really matter for this general point, and you study fluctuations, perturbations of the fluid, I mean, waves, or quasi-particles, or phonons. Now, the dynamics of the fluid affects, obviously, I would say, the dynamics of the perturbations. If your fluid is flowing very fast or is very dense and all of that changes the way waves propagate. That's a trivial fact. What is non-trivial is that the dynamics of the perturbations rather generically, I mean, I listed the assumptions there, but it rather generically takes the form of the dynamics of a complex scalar field on an effective curved geometry to which the perturbations couple. So the perturbations see an effective curved geometry, not the laboratory flat Minkowski metric in which you define your fluid system and your hydrodynamics. Again, this is a fact that you get this type of field theory on curved geometry, with the curved geometry being some function of the fluid density, the fluid velocity, but it's in a rather general form. You can simulate black holes, you can simulate cosmological phenomena at the level of quantum fields on a curved geometry. You reproduce the geometry by engineering your fluid to have the right density, the right velocity, and so on. So the right effective metric is produced. Then perturbations will couple to that, and you have a quantum field on a curved geometry. And there's a lot of theoretical developments, simulating black holes in the lab or in realistic fluids, simulating cosmological expansion and fields on an expanding universe, particle production in a cosmological setting. And there are even experiments claiming that, I think convincingly, that they actually reproduced and detected the sonic analog of Hawking radiation and exotic quantum semi-classical phenomena. However, the big open issue is that the gravitational dynamics of the type of general relativity is not reproduced. So you can reproduce the geometry and the dynamics of fluctuations on top of the geometry, fine. But the consensus is you cannot reproduce the gravitational dynamics. Why? Because there are structural limitations in the setup that I just described. The effective metric is in fact just a convenient rewriting of the fluid density and the fluid velocity. And they are governed by the hydrodynamic equations. Bernoulli equation and Navier-Stokes and all of that. Okay, and those equations are background dependent. There is the metric of the lab on which the fluid is defined. They have preferred frames, and they have some special global symmetry, the Schrödinger symmetry that I mentioned earlier, for example, or just Galilean symmetry for your non-relativistic classical fluid. Okay. And this is at odds entirely opposite to general relativity at the structural level, where you don't have preferred frames, you're background independent, you don't have special symmetries. But I've just shown you in the earlier part that in fact, that is not the case. That you can take hydrodynamics and it has the same symmetries, the same dynamics of GR in the cosmological sector. Where is how is the contradiction resolved? The point is that you shouldn't think of the hydrodynamic, according to what I said, you shouldn't think of the fluid or the hydrodynamic equation and the system being defined on a space-time manifold, because the manifold itself has no physical meaning because of diffeomorphism invariance. In general relativity, the manifold is just a convenient, redundant structure. You have to think of the same hydrodynamic equation defined on the space of fields, then compute appropriate relational observables, deparametrized observables. Those are the ones that will have to satisfy, if you've done things correctly, a gravitational dynamics and be matched with GR or some sector of GR if you are in specific settings. If that is true, then the task to proceed around the limitations, the structural limitations of analog gravity simulations is to change perspective. Don't try to reproduce a metric on a space-time manifold and its dynamics, but try to reproduce the superspace metric and all the right properties and the hydrodynamic equation on the superspace that are needed to match cosmological dynamics, like I did in the first slides. If that is true, then in principle, you can try then to look at realistic fluids which have that hydrodynamic that you devised in such a way, and see if they are realistic, if you can reproduce them in the lab, if you can do experiments, and which observable in the lab will correspond in this reinterpretation to some interesting cosmological quantity. So this is just to state again the four main points that I wanted to put forward in this talk. And this is to remember that we can be lucky. But even just the trefoil, which is pretty common, is pretty cool. And then is to thank you.
Thank you very much for this very interesting talk. So let's open it up for questions now.
We can pass around the microphone? Or?
Yeah, I think maybe I pass around mine. Do you take the questions from Zoom?
I can take the questions from Zoom, of course. Yeah.
And I start here. So, Simon?
Thanks for the talk. So I just want to make sure that I got the idea. So you have the superspace and then you have the fluid on top of the superspace. And this fluid is some kind of coarse-grained effect of something, some quanta of the superspace. And what is the physical meaning of that quanta of superspace? What is the ontology here?
Okay, I'm trying to translate your question in the usual quantum many-body physics setting. How would you answer that? I mean, I give you a fluid, I don't know, I swim in a lake, and then you come to me and say, look, this is the coarse-grained description of some atoms in some quantum many-body system. You even give me the quantum many-body physics textbook. And then you take it, you look at it, you say, okay, yes, I see how you can reproduce the behavior of the fluid, and I'm swimming in, and I'm observing, and I have experience of, but what is the ontology of your atoms? Now, how do you, as a physicist, how do you answer that? As a physicist, you try to derive properties that either already detectable at the fluid level. So in our analogy, in our case, it would be modifications of the GR dynamics or some aspects of the GR dynamics that you can directly trace back to the presence of these atoms. And you would say, well, their ontology is manifested in these observable effects. Or you could, so this is what I think a physicist would first do. Then you can try to see if changing properties of those atoms will change radically these effects. That means that you constrain the ontology of the atoms to be of a certain type. They have to have some properties, otherwise the theory will be wrong. Your model is a wrong model of the world. At this point, the physics normally stops. And then you can keep asking, okay, but what is the ontology of those atoms? But then it's not a physics question. Then what I can answer is, well, then is a very general question about models of quantum gravity or quantum gravity frameworks in which space-time, fields, and that are not fundamental. There is something else. And then I would say that you have to redefine or extend a number of notions in ontology, even leaving aside the physics, because they are not applicable anymore. If you define distinguishability as related to localization in space, or the fact that you can separate in space things, or the space-time influence to one another, well, that is not available. If you define existence as persistence in time of certain properties of certain systems, that is not available. Then you understand why, if I try to answer your question at the purely philosophical level, I have a tough job, because I don't have the categories of ontology to answer the question. They have to be redefined first, and then I can apply them to the new suggested structures. Normally, I stay at the physics level, but since you ask.
That's a question by what, I think.
Yeah, but maybe you keep the microphone, otherwise we get.
Okay, so what, please go ahead.
Okay. Hi, Daniele. Thanks for the lovely talk. Yeah, I have a. It's also a conceptual question. I'm not sure it makes sense too, but you don't hear me very well.
Yes.
Then we should repeat the question.
Is this better?
Yeah.
Better.
You hear me?
Yes. Yes.
Okay, perfect. Yeah, it's a conceptual question as well. So not sure it makes sense even, but like I have some familiarity like with mini superspace, quantum cosmology, and then you have to think about the wave function really as like describing a single universe. Okay, so you really get into this problem of if I do statistics with a single wave function, what is it telling me about our universe? Okay. That's contrary to quantum ordinary tabletop quantum experiments, right? Where you have many systems, you have an ensemble of systems, and then you do experiments, and you can look at the statistics and all that. And now, so here, if you say that like your hydrodynamic approximation gives you something like the Gross-Pitoevsky equivalent of mini superspace quantum cosmology, do you somehow have the same worry, or in the sense of how should I interpret my wave function now? It satisfies some Gross-Pitoevsky-like equation. And you also know like Gross-Pitoevsky itself, it applies really to a collection of of systems, right? A collection of bosons in your
Okay.
condensate. So the worry in short is like, if you take statistical, if you take averages and all that, are you sure this is telling something about our universe or not? Or
Okay. So let me rephrase the question for whoever didn't hear first, and then just to make sure that I understood the question. So the question was, well, first premise, in ordinary quantum cosmology, the interpretation of what you're dealing with is a bit ambiguous or puzzling, or some people are not convinced, because you're adopting a statistical interpretation in terms of probabilities and so on for your quantum system, which is supposedly describing the whole universe. So it's unclear. Well, you mentioned just the statistical aspect, you don't have an ensemble, but there is also another aspect that is specific to quantum mechanics, having to do with the quantum collapse, and what does it mean to have a wave function and a Born rule for the whole universe, and a probabilistic distribution of outcomes of experiments, given that nobody does experiments on the whole universe and the wave function probably doesn't collapse. Okay, that's one part of the story. And the question was, what changes in this nonlinear extension of quantum cosmology, or in this Gross-Pitaevsky hydrodynamic reinterpretation? Okay, the answer is, okay, as in many other cases, the basic answer is I don't know, but the next to leading answer is that, well, some problems are probably of the same type, because you try to take literally what is going on here, and you have some state for the universe, for literally here, a particular state for the whole constituents of the universe, these discrete building blocks coherently superposed. Collectively, they are described as this hydrodynamic equation, but you have one universe with one ensemble of building blocks, and you have a coarse-grained description of their dynamics and their physical properties. So just like you have a single Bose-Einstein condensate in your lab, in your bucket of liquid helium. Now, I've never been to a condensed matter lab, but I imagine them to have a bucket of liquid helium on the desk that they look at, and that's the experiment. I suspect this is simplified, but anyway, they have a single system there that is, in fact, is composed by some super large number of atoms, but they are collectively described in a very simple manner by this Gross-Pitaevsky equation. So I would take a very similar perspective here. You have, your universe made out of many constituents at some microscopic level of description, but collectively is described as such a condensate wave function, which is a fluid density and a fluid velocity on superspace, and some dynamical equation. So from this point of view, you could say it's as tricky as in quantum mechanics, because you would be led to adopt a statistical interpretation, like you do for fluid dynamics. There are microscopic constituents, but you have some average statistical description. But you cannot really have an ensemble of such systems. You can just have an ensemble of guesses about what the system is at the microscopic level, and go with that. So in this aspect, in this respect, it's very similar to quantum cosmology. This aspect, I would say, is equally puzzling, or it requires some work conceptually. On the other hand, I stress again, at this level, you don't have superposition. You don't have a Hilbert space. Your wave function is just a coarse-grained description satisfying a nonlinear equation. So there's no Hilbert space of solutions. There's no Born rule. There's no linear superposition principle for configurations of the universe in this sense. So some problematic aspects of quantum mechanics applied to the whole universe at once, like in quantum cosmology, are absent here. Quantum mechanics here is applied with quantum fluctuations, entanglement, Heisenberg principle, all of that to the constituents, to the microscopic discrete building blocks. And there it remains problematic, maybe, as you know, from the foundations of quantum mechanics, but at that level, at this cosmological level of approximation, you have really like a coarse-grained, fluid, nonlinear description. So it's different. Does it help, Ward?
Yeah, surely. But
You have
I would
to
have
say
thought
yes,
that.
otherwise I can keep going for another 10 minutes.
No, but I
answering
would
the
have
same
thought by,
question.
yeah, I would have thought by taking these expectation values and all that, you're kind of assuming some kind of form or not. Otherwise, what's the meaning of these expectation values?
Yeah, but these are hydrodynamic densities, right? So you know that so if you assume that you can have an ensemble of this type of system, not necessarily because you physically prepare an ensemble, but because you're dealing with a coarse-grained description of microscopic degrees of freedom that you don't touch directly, then you adopt a similar conceptual scheme. I'm not saying it's not problematic, but it's a different type of problem than in quantum mechanics. And some specific aspects of the quantum mechanical challenges, like linear superposition and interference, are just absent here.
Because I thought you were taking the averages also like by integrating over the scale factor.
Yes, but the average
so then you're not
computed at the hydrodynamic level.
Okay.
It's really just average quantities computed with your fluid density, as you would do in a hydrodynamic. So it's more of a statistical type of interpretation, but not because there's no quantum mechanics at the fundamental level, but exactly because quantum mechanics applies to the fundamental degrees of freedom, but not at this directly this coarse-grained level.
Okay, thanks. So there's another question. Otherwise, people assume they don't do.
I really have to tell you, before you leave, you have to come to Schellingstrasse one day. It's not in my group, but there are, I guess, 5 or 6 experiments with Bose-Einstein condensate. Buckets. None.
You have a bucket. I can finally see the bucket.
It's helium. Because liquid helium will never get that cold what the atom.
Okay. I suspected also that part.
Anyway, what I was wondering, I mean, you say the nonlinearity, which is, I guess, essential in all hydrodynamics, it comes from coarse-graining. Coarse-graining to me something like an approximation. It's more a mathematical step or whatever. So it doesn't have to do anything with interactions now, what is typical for hydrodynamics. So you don't have interaction. It's just that due to some approximation, a similarity in the equation pops up, or is it?
Yes, well, yes and no. I mean, in the Gross-Pitesky nonlinear term is directly what corresponds to the scattering term for the atoms of the system. So it has to do with, is the classical result at the coarse-grained level of the fact that they interact.
Describe some cosmological structure, you do not have interaction, but...
Well, what I'm saying is that, the effective description, yeah, so my statement is, just like the Gross-Pitesky hydrodynamic equation as a nonlinear term, which is the counterpart of the fact that the atoms are self-interacting, in fact. In this case, there is a nonlinear term in the effective hydrodynamics on mini superspace coming from the interactions of the tetrahedra, of the quantum building blocks. In this sense, it's an exact correspondence. Now, so this nonlinear equation becomes then an equation for observables like the scale factor and so on. This equation, depending on the approximation, may have different type of interactions. But in general, you expect this type of self-interactions to give nonlinear terms also in the equation for observables. It doesn't necessarily mean that localized systems at large scale in the universe have an interaction in space-time. That may not be the case. I'm just talking about these global quantities like the scale factor, the average Ricci curvature. I mean, this type of cosmological observables satisfy in general nonlinear equations and coupled. That's the statement.
Okay, so we have another question.
I would like to ask a question. Daniele, thank you very much for the nice talk. I have a similar question. I mean, I have two questions, but one is more stupid than the other, so I'll try to ask the less stupid one.
No, start with the clever one.
This is private.
Okay.
So let's see how much time we have. So I hope the less stupid one goes a little bit in the same direction. Gross-Peter is somehow a certain limit, a thermodynamic limit, if you like, of the Drusen gas with an interaction. Yeah?
Weakly interacting, there are a number of assumptions. You have to be
exactly, yeah.
Small densities, weak interactions, and I don't remember what else.
Exactly, and there are other regimes, for example, the Hartree-Fock mean field regime, and so on and so forth. And my question would be, does the Gross-Peter for your program somehow stand out of this multitude of, let's say, n-particle approximations?
No, it stands out just being the simplest one.
Well, mathematically, the Hartree-Fock is much easier to handle. Yeah.
Well, if you just look directly at the atoms, but the most coarse-grained level, the first thing you would get is the simplest state is a coherent state for the atoms, and that will give you the Gross-Peter. The moment you start introducing correlations between the atoms, which are not, so they're not just superposition of product states, then you have a correction to the Gross-Peter dynamics, and that is more complicated. So in this sense, it stands out because the simplest thing you can write down, starting from the definition of the model for the atomic degrees of freedom, the simplest hydrodynamics you will write down is Gross-Peter. In this sense, it stands out, and it's very nice to you. But it's clearly not realistic. I don't believe that again, I have several condensed matter physicist friends, but we tend to talk about other stuff. I would imagine that nobody really believes that the atoms in a Bose condensate are actually all there with the same wave function without actual further correlations between them and modifying the product structure or the wave function for given n. Exactly. So the only statement here is that a decent approximation, if God allows, of the actual ground state of the system is given by this Gross-Peter dynamics. And then you start improving.
The fact that you use the building blocks, the analogy of an in-particle Bose gas and not a Fermi gas.
No, there are people who have studied also fermionic statistics, but first of all, stuff becomes more complicated for a number of reasons. Nobody has really tried to extract the corresponding cosmology from these fermionic models. So I don't know how much changes of the dynamics I discussed at the cosmological level. That I don't know. And the bosonic statistics is an assumption here. It's not really derived because it is at the level in which we don't have preferred space-time metric and directions and so on. We don't have the spin statistics theorem. So we don't even know whether we should use bosonic statistics given a certain symmetry. That tool is not available. So it's purely an assumption. It's just the simplest statistics you can consider here. And it's compatible with all we know from the point of view of lattice gravity, the various motivations for these models. This was the clever or the stupid question?
The less stupid one. My stupid question.
I thought I'm done with the difficult. Okay.
So Walk has another question. But,
Is there another question? I think
you were first, right?
You took the Greek group field theory as the fundamental theory. To derive the hydrodynamic approximation, you took the mean field approximation, this gives you a condensate. And from there, what are still the assumptions you need to get the Gross-Peter type approximation? I mean, they need to be.
No, well, the hydrodynamic equation we get is the Gross-Pitayevsky, assuming that you can neglect one loop, two loop, three loop corrections to the hydrodynamics. And so that you are weakly interacting small density and so on. Yeah, exactly. The simplest approach. If you make this approximation that loop effects can be neglected, then you get the Gross-Pitayevsky. Yes, then you get the Gross-Pitayevsky hydrodynamics. Otherwise, you would have to correct it with additional terms. Yeah, that's the same. No, it's the same. I mean, you can take a spin-form model, write it as a group field theory, and proceed. Of string theory? No, of course, but it's just that the language is very different, so I wouldn't know exactly how to apply the same scheme. I mean, loop quantum gravity spin forms, I can phrase them in the same formalism, in the same language, so I know what differences I have to focus on, what I should adjust. But string theory is a very different language, so I wouldn't know exactly how to translate. I have nothing against it, just that I wouldn't know how to compare.
What is another incident? So let's have these two and then.
Thanks for your talk. So I want to explore the analogy a bit more with your psi a phi and the Gross-Pitayevsky equation. So I was a bit confused when you were applying to what that you don't have Born rule. So my understanding was even the Gross-Pitayevsky equation has the Born rule up there.
Born rule
I1 is a conserved quantity.
Yeah, but Born rule would mean that you are in a certain condensate state, say psi a phi. You measure your system, you get A with a certain probability, you get A prime with a different probability, and so on. This is not how you do hydrodynamics. In hydrodynamics, it's not what the wave function means. I mean, the wave function is just the distribution that allows you to compute hydrodynamic averages, and that's what you measure. You go to a fluid, you check the average momentum, and that's the result of integrating over all possible values of the momentum for the particles with the distribution given by the condensate wave function. In that sense, that is not, it doesn't have a probabilistic interpretation for individual measurements.
So my real question is, so you have.
But what was that?
So that was just a clarification.
Just to warm me up.
What you meant by Born.
Okay.
So my question is
there was the tricky, there was a trap. I first relax and then question.
So now you have this, so you said like this I1, I2 to I, so you have 4 of them and the Gross-Pitayevsky. I somehow took the message to be, so you have now the nonlinear equations for the I's and then you have the original nonlinear PD for the psi. And were you suggesting that getting all the I's is equivalent to getting the psi, the original psi?
Yes.
So this I didn't get because I thought you lose something about psi when you integrate over R. So how do you reconstruct the psi from the R's?
So first of all, it's the psi plus a number of conservation laws. So it's a number.
Follow from the Gross-Pitayevsky equation, I would presume. Because equation stands on its
some
own.
of them follow, yes.
I thought all of them follow from the equation.
So definitely it's clear that if you have a solution of Gross-Pitayevsky, you can get a solution you can get all the I's. Now you're asking the inverse problem.
I think the inverse problem is simply if you have a random variable, you know all the momenta of the random variable, and you know the distribution of the random variable.
Yes. So it's not that you necessarily reconstruct the psi, but you reconstruct the dynamics of observable properties of the probability distribution for observable properties. And that's that. But it's not that I checked the papers on this aspect. There I trusted what I read in the papers.
Because that would make the life much easier. You just solve for 4 functions of time, couple nonlinear equations, and you get full psi.
And I'm not sure how easy that is, but yes.
No, it's much easier than solving a PG. Solve 4 ODs.
Yeah, I would guess so.
Anyways, we can talk about it.
Thanks. So let's have the last question by Rob.
Okay.
What so? Please.
Hi again, yeah. This is a question about like the motivation or the embedding, as you said, like within quantum gravity models. So suppose I start from Wheeler DeWitt with all the degrees of freedom. Could you like motivate, maybe heuristically, that you would get to this hydrodynamic picture or not? Or
so the motivation for looking for some microstructure that is not given by the metric field?
Well, or let me rephrase it. Like, it's a question how to get like mini superspace Wheeler DeWitt from full Wheeler DeWitt. Okay. Your work, would that be a kind of route to that? Like, of course, this you get this gross Betaevsky, right? So could you
yes,
like say, I start from full Wheeler DeWitt, I do some approximations, mean field like approximations, and then I can motivate ending up with.
Okay, so if I take I take just the perspective from within quantum gravity. Why all this from the point of view of quantum gravity, regardless of hydrodynamics and so on?
Well, I take one specific here now, just for definiteness, like Wheeler DeWitt, but it could also be, well, I don't know if that exists, but like full loop quantum gravity. Like mini superspace, we know that this is an ad hoc assumption, right? So we know there have to be corrections to that. And is there a certain recipe you can follow using mean field techniques of ordinary quantum field theory that would justify your hydrodynamical modification of mini superspace starting from the full Wheeler DeWitt theory?
Yes. Okay. So if you take the perspective that quantum gravity is the result of quantizing general relativity, then your fundamental theory is going to be indeed the full Wheeler DeWitt, as you call it. So you have a linear operator equation with some Hilbert space of solutions, and that's states of the universe. Your fundamental degrees of freedom are the quantum geometries, the quantum metric field up to diffuse. And you may ask, okay, but if I want to go to a reduced, symmetry reduced cosmological sector, which would correspond to mini superspace and usual quantum cosmology, how do I do that? And that is interesting mathematically, but it also required if you would like to trust the predictions of quantum cosmology, because in order to do that, you need to embed it in a more fundamental theory and see how observations will constrain the fundamental theory in this approximation. This is not the perspective I take and not the perspective I believe in. The work that I discussed is motivated by the idea that the fundamental theory is not obtained by quantizing general relativity with the same degrees of freedom turned quantum. In that context, you would have indeed the problem of a classical limit, but you would have no problem of collective dynamics or coarse graining and so on. You have in case the inverse problem of symmetry reducing the theory to special sectors. This is the problem you are referring to. I don't know why I'm indicating the screen given that I didn't turn on the camera. But the perspective I'm adopting is the one that I tried to introduce earlier, which is you have some other degrees of freedom, which are not the metric, classical or quantum. They may be quantum themselves, but you need some coarse graining, some averaging, some collective effect to produce a classical or quantum metric with or without any symmetry reduction. So I take this perspective seriously. I work in a given formalism where the perspective is realized. I ask what is the simplest coarse graining I can think of, and what is the simplest coarse-grained dynamics. I obtain this non-linear extension of quantum cosmology, hydrodynamics and superspace, without taking classical limits, just taking this mean field coarse-graining approximation. And then it turns out that at this fully coarse-grained level, it has just the variables of quantum cosmology, but with nonlinear dynamics. And then I can ask how I reduced to standard quantum cosmology. When is it that the nonlinearities are relevant? When instead I can just think of a linear equation on the wave function. But it's a different type of procedure and perspective than the one that I would try to apply after quantization of general relativity. Does that help?
Yeah, great, thanks. Excellent. Yeah.
So I think, as we are already far over time, it's time to end here. So thank you all for coming. Thank you again. Thanks to the speaker. And so I wish you a good Christmas holidays for those of you who I don't see again, and let's meet again in January. So next talk is Daniele Oriti from the Technion Haisa in Israel. And yeah, we will talk about typicality, probably. Okay, and then afterwards we have Daniel Sudarsky.